Hi everyone, I demonstrated in class yesterday how we arrived at 7.67 meters per second for that first answer there. But we're back to the metal hoop, and I'm going to solve for the velocity at B. If the initial velocity is 10 meters per second, the velocity at C, and the maximum compression of the spring. I'll show you how to do that. So with initial velocity here of 10 meters per second, it will have kinetic energy plus potential. So UGA plus kinetic energy at A. But it's also rolling, so there will also be some rotational kinetic energy at A. Mark that with a KAR. At position B, there will be no potential energy left. There will only be translational kinetic energy and rotational kinetic energy. This is at point B. So we start out with a height of 6 meters, kinetic energy with a velocity of 10 meters per second, 1/2 mv squared. Now the rotational kinetic energy is that I omega squared, where the I is of the hoop, mr squared, and since V equals R omega, that means that omega equals V divided by R. So we're going to substitute, instead of 1/2 I omega squared, we're going to use V over R squared. I'm going to go ahead and square those two. Just a little side note, this is coming from rotational kinetic energy equals 1/2 I omega squared. So I substituted the I, I substituted the omega squared, being V squared over R squared. So there they are. And that's the beginning of the equality. After it reaches point B, then the kinetic energy will be 1/2 m velocity at B squared plus 1/2, again, here we'll have mr squared times velocity at B squared over R squared. And I was just noting that I forgot the little velocity A over there. So we got this equals that, before at point A and after at point B. We're going to have some masses cancel and some other things cancel out of this. The R squareds will cancel. Thankfully that gets rid of those values. Masses cancel throughout, because if we divide one side by m, divide all the terms by m. And so we'll have a G is 9.8 times 6 plus 1/2 of 10 squared, that's the initial velocity, is 100. And we're left with 1/2 of, again, velocity at A, that's also 10. So that'll also be 100. There's the contribution of the initial rotational kinetic energy, equals 1/2 of VB squared from this term, and also we're left with a 1/2 of VB squared over here. Alright, I'll move that up a little bit. We've got a 58.8 plus, here's 1/2 of 100 is 50, plus 1/2 of 100 is another 50. 50 plus 50 is 100, equals 1/2 plus 1/2 is a whole. That conveniently makes it VB squared. So 158.8 equals VB squared, and we get the velocity at B being the square root of 158.8 12.6 meters per second. Quite a lot to go through, but there it is. What can we learn about C then? The only difference is we've got some potential energy at the end here. So we're not stopping at the bottom. We're coming back to a higher height than we started at. So back here in this step, we started at 6 meters, but we ended up with basically at a height of 0. So we're going to add on back up in this step. we get an mg height at b. So since the masses would cancel there, we're going to add on a 9.8 for the g, and a height of b is 10. So to solve this next part, I'm going to add on that 98 joules of, well, I guess it wouldn't be joules because it canceled the mass out, but 98 is the contribution there. So from this step on, that's the only difference here, is that at point C, where you've now got potential energy. So the effect would be taking the 158, and we're going to subtract out 98 from that for the second part. So 158.8 minus 98 would be now the VB squared. And so it leaves us with, what would that be, 60.8? Hope I did my math right there. I'll take the square root of both of those. Oops, I messed up there. Square root 7.79, or we'll say 7.8. There it is. 7.8 meters per second. At point C. Okay, so it is slower than where it started at point A, because it's up at a higher height. So it's slower than at point A. All right, what about that compression though? Well, mass is going to be important here. It says it's a 3 kilogram metal hoop. And there's a couple things I can do. The energy at any one of these points, A, B, or C, will also equal the energy at D. So what do we have here? If we started with the energy in the beginning, we had potential energy in the beginning, we had translational kinetic energy, of course this is all at point A, and we had rotational kinetic energy. Here at the end, everything's going to be stopped, but it's still at a height above the ground. So we're still going to have some gravitational potential energy. It's going to be compressed, so we're going to have, the spring is going to be compressed, so we're going to have some elastic potential energy at B. But what denotes the maximum compression of the spring is that the ring is going to come to an absolute stop. At that point, the spring will be compressed to its maximum value. So if we tried to add in some kinetic energy here, just note that it's going to be 0. That's what will denote the maximum compression of the spring. Okay? So let's go back in time here a little bit. mgh, height at A, plus half mva squared. And you might remember that out of this we had 1/2 mr squared times va squared over r squared. We ended up with a 1/2, and I did cancel out the m's, but the r's canceled, so we'd have this 1/2 mva squared. We don't want to cancel out the m's this time. So the rotational contribution there, the kinetic energy, is 1/2 mva squared, just another term like that. And at this point, we've got a mass times 9 times, let's keep it as g, times the height. Oh, my apologies, we are at point D. There we go again. At point D. So this will be gravitational potential energy at point D plus the elastic potential energy at point D, which is 1/2 kx squared. So this is what's going to give us our maximum compression at x. That is at point D. All right. So let's do this. We've got 3 kilograms, G is 9.8, and at height A, 6 meters. Now if we combine these two, 1/2 plus 1/2 is a whole, that'll give us mass times velocity to A squared, which is 10 squared. So it's 1/2 mv squared plus 1/2 mv squared is mv squared, equals 3, G is 9.8, Height at D is 10. And we've got a 1/2. Now the K value, the spring constant, defines on the front page as being 100 newtons per meter. That's our K value. Not big K, not kinetic energy, but little k, that spring constant. So moving back to the correct page. Woo! So spring constant, 100 newtons per meter, and our unknown compression distance. There it is. So we've got 3 times 9.8 times 6 plus, there's 300 there, 476.4 equals 98 times 3, 294, plus half of 100 is 50, xd squared. So subtract 294 from 476.4, you get 182.4 equals 50 times xd squared. Divide both sides. 3.648. 4. And our distance then would be the square root. .91 meters. There it is. 1.91 meters. And that's all there is to it. Now for the rest of this, the graphing, we're focusing on this. What's going to be happening to potential energy? What will it look like? Well, potential energy, keep in mind, there's gravitational and elastic. Zoom in here a little bit. Focus. All right. So gravitational elastic, we're looking at this entire trip. So there's no elastic potential energy until we get to the spring, which is somewhere around 50 meters. Just a little bit before that. At that 50 meter mark, what will happen there? A little bit before, it's going to start compressing. But before that, potential energy only depends on the height of the ramp. So potential energy should just follow that height. It comes down, not quite to 0, and it goes back up before 25. It goes to a higher height. And a little bit before 50, something happens. The gravitational potential energy stays the same because the height stays the same. But when that ring is going to contact the spring's potential energy will increase. So we're going to see, strangely enough, an increase here at the end. Okay? So there's a potential energy curve, something similar to that. Should match the shape until the very end when it spikes from that spring potential energy. There's a little spike at the end from the spring. Okay. What about the kinetic energy? Well, our kinetic energy is made up of rotational and translational. Just think about it as the motion. The motion increases, and it decreases, and it will remain constant. And at the very end, what happens? The motion comes to an end. So we should end up at 50. At the 50 meter mark, we should have 0 kinetic energy left. We should also have a starting kinetic energy. It's not starting at rest, so it is moving to begin with, but it'll be moving faster here in the beginning than it is at point C. So the kinetic energy will be increasing. Let's start it out. So I got to think this through too. So it's going to increase till it gets to B, and it'll decrease again at around point C, somewhere around right here, it's going to be going slower than it was to begin with, and then towards the end, when it hits that spring, it's going to drop off. So something sort of like that. Notice it's rather opposite to the potential energy. All right. What do you suppose the total mechanical energy is going to look like? Well, when kinetic energy is 0, the potential energy is at its maximum. So how about that total? It means at the very end, 0 plus a maximum will give us a maximum up here. However, we see some changes happen. As potential decreases, kinetic increases. But what overall happens to the total mechanical energy? It stays the same.